Our universe, vast and enigmatic, holds secrets that have captivated the human imagination for millennia. Yet, there remains a realm so strange, so counterintuitive, that it seems to defy the very logic upon which our everyday experiences are based, the quantum realm. Here, particles behave like waves, and waves behave like particles. Objects can exist in multiple states at once, their fates intertwined in a cosmic dance of entanglement. Join me on an exhilarating journey into the heart of quantum mechanics, where we will explore the mind-boggling concepts that underpin this strange and wonderful realm. The dawn of the 20th century marked a turning point in the history of physics. This was the birth of quantum mechanics, a revolutionary theory that would forever alter our understanding of the universe. Classical physics, with its elegant equations and deterministic predictions, had reigned supreme for centuries. However, as physicists began to probe the realm of atoms and subatomic particles, they encountered phenomena that defied explanation within the classical framework. Light, for example, sometimes behaved like a wave, while at other times it acted like a stream of particles, tiny packets of energy called photons. These puzzling observations forced physicists to abandon their classical intuitions and embrace a radical new way of thinking. In the quantum realm, the future is not preordained. Instead, it is a tapestry of possibilities, woven together by the intricate dance of quantum probabilities. At the heart of quantum mechanics lies a profound paradox wave-particle duality. This principle asserts that all matter exhibits both wave-like and particle-like properties. Imagine a beam of light passing through a narrow slit, creating an interference pattern, a hallmark of wave behavior. But how can light, composed of particles called photons, also exhibit wave-like properties? This is the essence of wave-particle duality. This duality extends to all particles, including electrons, atoms, and even molecules. In the famous double-slit experiment, electrons fired one at a time still formed an interference pattern, as if each electron were interfering with itself. Quantum entanglement is a phenomenon where two or more particles become linked, even when separated by vast distances. The state of one particle instantaneously influences the state of the other, regardless of the distance between them. Einstein famously dubbed this spooky action at a distance. Imagine two electrons born together and then separated, each placed in a box. These electrons are now entangled. If we observe the spin of one electron, we instantly know the spin of the other, even if it were light years away. This instantaneous correlation has puzzled and intrigued physicists for decades. Entanglement arises from the fact that in the quantum world, particles do not have definite properties until they are measured. The concept of superposition lies at the heart of quantum mechanics, challenging our classical intuitions about reality. In the quantum world, particles do not exist in definite states until they are measured. Instead, they exist in a superposition of states, a kind of quantum limbo where they possess all possible values simultaneously. Imagine a coin spinning in the air, neither heads nor tails, but in a blurry state of both possibilities at once. An electron orbiting an atom does not follow a well-defined path, but exists in a superposition of all possible positions at once. It is only when we make a measurement that the superposition collapses and the electron chooses a definite position. The act of observing the quantum world forces it to choose one reality from among the many possibilities. Schrödinger's cat illustrates this paradox. Until the box is opened, the cat is in a superposition of states, both alive and dead simultaneously. Quantum tunneling allows particles to pass through energy barriers that, according to classical physics, should be impenetrable. Imagine throwing a ball at a wall. In the quantum world, the ball has a chance of simply disappearing on one side of the wall and reappearing on the other. This bizarre behavior is a consequence of the wave-like nature of particles. Just as a sound wave can travel through walls, a quantum wave can extend through an energy barrier. Quantum tunneling explains how nuclear fusion, the process that powers the sun, is possible. Protons in the sun's core can tunnel through the energy barrier, releasing the energy that sustains our star. Quantum tunneling plays a crucial role in many technological applications, from transistors to scanning tunneling microscopes. Without quantum tunneling, our technological world would look vastly different. The Heisenberg uncertainty principle states that there are fundamental limits to the precision with which we can know certain pairs of physical properties of a particle simultaneously. The more precisely we know one property, the less precisely we can know the other. This principle is not about the limitations of our measuring instruments, but a fundamental property of nature itself. One famous example is the relationship between a particle's position and momentum. The more precisely we know a particle's position, the less precisely we can know its momentum, and vice versa. The uncertainty principle tells us that at the quantum level, the universe is inherently probabilistic. We can predict the probability of finding a particle in a particular location, but we can never know with absolute certainty where it will be. This inherent uncertainty is a reflection of the fundamental nature of reality itself. Quantum field theory combines quantum mechanics with special relativity and field theory, providing a more profound description of the universe. In this framework, particles are not seen as fundamental entities, but as excitations of underlying quantum fields. Imagine a vast ocean, its surface constantly rippling with waves. The waves are disturbances in the underlying fabric of the ocean. Similarly, particles are seen as ripples or excitations in underlying quantum fields. These fields are present everywhere, even in the vacuum of empty space. The electromagnetic field, for example, is a quantum field whose excitations are photons, the particles of light. Quantum field theory is the foundation for the standard model of particle physics, describing all known fundamental forces in the universe except for gravity. The future of quantum mechanics is brimming with potential, promising to revolutionize fields from medicine to computing. Quantum computing harnesses the principles of superposition and entanglement to perform computations impossible for classical computers. Quantum bits, or qubits, can exist in a superposition of both states simultaneously, allowing quantum computers to perform multiple calculations at once. This massive parallelism could revolutionize fields like drug discovery, materials science, and cryptography. Quantum communication exploits the principles of quantum mechanics to enable secure communication channels. Quantum technologies are poised to revolutionize fields like medicine, enabling more precise imaging techniques and targeted drug delivery systems. Quantum sensors could lead to breakthroughs in medical diagnostics, environmental monitoring, and fundamental research. Our journey into the quantum realm has taken us to the very edge of human understanding, revealing a universe far stranger than we could have imagined. Quantum mechanics has challenged our classical intuitions and forced us to reconsider our place in the cosmos. Despite its counterintuitive predictions, quantum mechanics has proven to be one of the most successful scientific theories ever devised. As we continue to explore the quantum realm, we can expect even more surprises and challenges to our understanding. The quest to unify quantum mechanics with general relativity remains one of the greatest unsolved mysteries in modern physics. As we delve deeper into the quantum world, we may find that the universe is not only stranger than we imagine, but stranger than we can imagine.